So as we move into dealing with continuous probability distributions, we're going to start with a uniform probability distribution. And the moment we talk about uniform probability distributions, the mental picture I want you to think of is this kind of square or rectangle. Again, we're starting here with these types of distributions because it helps us really quickly and easily understand that as we deal with these distributions, we can find, we can quickly show that this relationship exists between the area within this distribution, the percentage of values that we would find there, all right? So I'm going to do this by looking at an example in our Alexander Holmes OER textbook. Specifically, I'm looking at from chapter 5, example 5.2, and it says the amount of time in minutes that a person must wait for a bus is uniformly distributed between 0 and 15 minutes inclusive. Okay, and so I'm going to use this kind of given information as a starting point. I want to talk about a few things beyond just the question that Dr. Holmes poses. He basically asks one question. He says, what is the probability that a person waits fewer than 12.5 minutes? So we're going to build our way up to answering this question. But basically he's saying, what is the probability that an individual waits fewer than or less than 12.5 minutes? So he's asking us to whether x is less than 12.5 minutes. Okay, and we're going to get there, and there's a couple of things I want to talk about first. So when we look at this distribution as we describe it, in the previous definition we talked about, I mentioned that the probability density formula for these uniform probability distributions is very simple. So this probability density formula is very simple. In this case, our probability density formula is basically, this description of this distribution is very straightforward. It is 1 over b minus a. Okay. Now, just because we're talking about this distribution in minutes, we've got to kind of step back for a minute too. We're not talking about a discrete value here. We're talking about a continuous value, because what are we describing here? We're describing time. And time is a continuous variable. All right. We can infinitely measure, all right, time in terms of the increments. It is a continuous value. Okay. The probability density formula for this one, unlike, for example, our normal distribution formula, is very, very simple. Okay, when we get into our Gaussian distribution, our normal distribution, we'll find that to be a whole lot more complicated. If we want to find this, then probability density formula for this particular distribution, the way that we're going to show this is our minimum value is the A, our maximum value is the B. This probability density formula is then going to represent the height of the probability distribution. So if we're looking for the height of this particular probability, or this continuous probability distribution, we're simply going to go in and go 1 divided by, we have our 15 minus 0 gets us to 1/15, which is kind of a strange number, but that is then also the height of this uniform probability distribution. If I want to show, and he mentions in the problem that 0 and 15 is inclusive, if I want to show that the total area of this distribution is 100%, or it includes all of the possible outcomes, to find the area within any square or rectangle is basically then just my base times my height, right? My base times my height. Area equals, this is not the same as B, in this case the value is, but really I'm looking at the base value times the height, okay? So if I look at the total distribution, my base, how wide is it? It's 15 minutes. Times my height, 1/15, gets me to 1.0, or this stands in for this idea that I'm absorbing 100% of all of the possible outcomes with this uniform probability distribution, all right? We can also calculate the average and the standard deviation of this uniform probability distribution. The issue with calculating the average, which I'm just going to call it out right now, is right here at 7.5, is that doesn't describe much. If we look at a normal probability distribution, there is some value at looking around this measure of central location, but here there's just not much going on. My average doesn't really describe this distribution any better than any other individual value. If we look at the standard deviation as well, and we get into normal distributions and we look at that standard deviation, it's also going to be very telling. We started looking at that when we went in to our descriptive statistics area, looked at Chebyshev and the empirical rule. And if you remember that, we were really concerned with how far away and the number of standard deviations we were from the mean. Okay, so the mean had some value in those examples as well. But for the uniform probability distribution, it really doesn't describe much. So in this video, I'm not going to go into that to a lot of detail there because they're not overly value added. But what we can do is we can use Dr. Holmes' original question to start to illustrate how we would go about doing things and the value in these uniform distributions. So if we want to go back to the original question here, what is the probability that someone will be waiting then less than 12.5 minutes? We want to find out what that area is. If I want to find any area within this uniform probability distribution, again, it's my base times the height. The base here is 12.5, right? 12.5 times my height, which is 1/15. If I take the 12.5 divided by 15, I end up with 0.83, lots of threes, I would imagine, 833, or right around 83%. So in this case, what we would do is go in and say, well, the probability now that an individual will wait less than 12.5 minutes, all right, is around 83%.